Welcome. So this is image formation, and in image formation we're going to do basically how we use rays to form images. So you study image formation to explain things like how do mirrors work and all that kind of stuff, but you'd also use it in light optics and electron optics and ion optics and a whole bunch of optics to find out where does the beam focus and where can I form an image and all this kind of stuff. And again, it's one of those things where the abilities are transferable. So if you get good at optics, you can kind of like you can apply it in different areas. First thing, you don't tend to draw things the way that you would intuitively draw things. You tend to draw things in a very analytical way. And so we've got to learn how to draw these diagrams. Let's take a simple case of just a plane mirror. We all know that a plane mirror gives you an image of what you see. So how can I show that? So let's say that I'm looking at an object that's above my head in a mirror. And so how can I, in light terms, kind of characterize what's going on? Well, the light comes from here and is reflected there, and then this guy comes here and is reflected there, and this guy comes from here, reflected there. And it works on the principle that for each different ray, the angle of incidence equals the angle of reflection. So it's pretty straightforward. It works by reflection. We know which law applies. Problem is, that's a really hard diagram to draw. And it's very hard to interpret. And if I had more than just one element, it would be a total pain. And so we develop a family of ray diagrams, and they've got certain characteristics. We define what's called the principal axis or the optical axis. That's the horizontal line. And then we invariably sit our object on top of that line. We don't look for a symmetrical object. We want the object to be from the principal axis up so that we can easily tell if our image is right way up or upside down. And then the idea is we'll take a few rays. Every point on this object has a billion rays coming from it. We just want to take a few rays. If we sit our object on the principal axis, we know that our image will be on the principal axis. All we need to do is find out where the top of our object appears to be. We can take two rays from the top of the object and we'll see where do they appear to cross. And wherever they appear to cross is where our image is. So I define the bottom ray. There's one ray. I know my bottom of my image must be on there. I take a top ray and I'll say, well, let's just take a ray from the top of the object going at 90 degrees to the mirror, and it bounces back on itself. And let's take a ray that's at some angle, but it reaches the mirror on the principal axis, and that will bounce back on itself. And I say, where does that ray cross that ray? Ooh, it doesn't. In fact, they're not converging, they're diverging. Oh. Well, they're diverging from a point. So let's back project them. And they appear to cross there. And so I can have what appears to be my image at that point. Wherever they appear to cross is where they appear to come from. If they had crossed, then that's where the image would be. Ooh. So a basic principle. I'm using two rays to define the top of my object because I know the bottom of my object is on a line. Does that make sense? It's a very efficient way of finding out what's going on. I'll typically use three rays to try and find out where an image is. Usually two from the top, one from the principal axis. And I'll ask myself, where do these rays appear to cross? Because that's where my image is going to be. Yeah? Sometimes the rays will actually cross. And that will be a real image. and sometimes the rays will not cross, but if you back project, they will appear to have crossed in another place, behind the mirror. There's no light behind this mirror. But when you look in a mirror, it looks like there's light behind the mirror. So when the rays don't actually physically cross, and you've had to back project one or both of them to a crossing point, there's still an image there. But it's not a real image. It's a virtual image. And then that raises the question, what the heck is the difference between a real image and a virtual image? And the difference is this. With a real image, you can take a piece of paper and stick it there, and if the light is bright enough and the room is dark enough, you will see the image. You can project it onto a screen. You take a magnifying glass and you take a light source, you can make a spot of light on the piece of paper. It's a real image. It's there. You can burn the wings off something if you're a 10-year-old boy. You can do something nasty, yeah? It's energy. It's real energy there. That's a real image. You can never do that by putting the fly behind the mirror. It's not going to happen because no light goes behind the mirror. And that is a virtual image. It still is apparent to you. It still is a thing. You just can't make it appear on a screen. So how on earth can you see it? Turns out you can see it because you've got this complicated optical system, which is your eye, which has a lens. I can display a real image, but I can't display a virtual image. But I can see both. And I can take the light from a real image and in my eye do stuff with it. And I can take the light that appears to come from the virtual image, which is, where's my pen? Which is that ray there and that ray there, and I can look at it and I can process it. So I can use real images as an object for a secondary optical system, and I can use virtual images as an object for a secondary optical system. So the difference between a real image and a virtual image is in some ways subtle and a nicety, because you can use both of them, so who cares? But in other ways, it's important because the math is different, and etc. Yes.
So if you have like a parabolic mirror,
Yeah.
Okay, and you're like a Dobsonian
Yep.
setup. Okay, so you got the light bounces off the parabolic mirror, and it meets at a secondary mirror.
Yeah.
Then you bounce it off again.
Yeah, you have a little plane mirror and you bounce off
That's
to your eye. Yeah.
not a real or fake image because you're gonna have it doesn't.
Oh, it's
they
real.
intersect, but they don't cross.
No, they do cross. We'll draw that out. We'll draw that out because that's one of the things
But
we're going to.
if it crosses, I mean the image is reversed.
Oh, that's another issue altogether. We'll get to that. just distinguish between real and virtual in a minute. Okay. So that's the game we're going to play. We're going to do it with plane mirrors, concave mirrors, convex mirrors, diverging lenses, converging lenses. That's the game we're going to play. We're going to do them graphically. We're going to do them mathematically. We need some terminology. So we call the distance between our optical element. Our optical element in this case is the mirror. The distance between the optical element and the mirror we call our object distance. We're going to give it the letter P. We call the distance between our image and the optical element our image distance. We're going to call that Q. if we have a height to our, if we draw this thing out and we have a height to our object, we can call it h. If we have a height to our image, we call it h dash. That's less important. Unfortunately, I think it was Newton who came up with these letters. And I can tell you now, Newton was not in the least bit dyslexic. Because I'll tell you, that and that drive me crazy.
Because the P is a reflected Q.
Yeah. And for instance, I never do multiple choice with you guys, but you know, if I ever do multiple choice, I have choice A, choice B, choice C, choice D. Because if I have A, B, C, and D, I mark B's wrong because I think they're D's, and D's wrong because I think they're B's, and it's a disaster. So just because the book has them in lowercase does not mean to say that you have to have them in lowercase. And I try not to have them in lowercase. Well, I try not to. But universally, object distance P, image distance Q. That's pretty well everybody uses those, you know. So what do we see for this, our first ray diagram? I can say that for a flat mirror, the image distance equals the object distance equals the image distance, and the image height equals the object height. And we can see that the image is virtual because the rays don't actually cross there. And I can see that the image is upright because it's standing up. You know, the top is the top and the bottom is the bottom. And because the image height is the same as the object height, the magnification is just 1. I can define, by the way, a letter for the magnification, which is big M. Okay. So, whoa, a little bit of terminology, and that's just to get us ready for it. It's like, you know. Let's look at and we're going to do this in lab today. I just changed the lab, actually. We're going to do this in lab today, so you'll see you'll get practice at it. Let's take a spherical mirror. We don't tend to deal with parabolic mirrors because although they're better quality, they work better, and they're not mathematically as straightforward, and just by tradition we do spherical mirrors. Spherical mirrors are easier to make, but they have some aberrations with them, which are kind of interesting actually in their own right. So we cheat, because if you take the middle bit, if I take that bit of a spherical mirror, it's well behaved. If I take that amount of a spherical mirror, not so well behaved. If I take that amount of a spherical mirror, bad. It's going to be really poor image. So if you can take a spherical mirror but only use a small section of it, you get a decent optical instrument out of it. But if you try and take a spherical mirror and use a lot of it, you know, a big angle of it, then it's not very good. And that's where parabolic mirrors come in much better, but they're harder to make. You know. So we're going to deal with spherical mirrors, and we have the principal axis. And then we have various points. We have the center of curvature. That's basically the middle of your sphere. And it's got a certain length, which is always going to the mirror. We have what's called the center of the spherical segment, V. It's the point where the principal axis meets your mirror. And it turns out that halfway between V and C is the focal point, which is really, 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 really important. I actually care about the focal point more than I care about the center of the spherical, rather than the center of curvature. It's like, it's the focal point that really, that I'll use for mirrors, I'll use for lenses, I'll use the focal point in all cases pretty much. Whereas the center of the spherical segment, center of the curvature is only used in a curving mirror. You know. Okay, so F is the focal point. I can talk about the focal length, which is that distance between the mirror and the focal point. If I draw rays parallel to the optical axis, and here this is a bad diagram, but I can't think of a better way to draw it. I'm showing a lot of curvature on this, and yet I'm applying idealized results to it. If I was to actually plot this and do the angle of incidence equals the angle of reflection, they would not all go through the same point. But I'm never going to use that much of a mirror. I'm only going to use that much of a mirror so I can cheat and get away with it. But to draw it, I want to draw it so you understand it. So I draw much bigger, curvier bits than I really should. But when you use the small bit in the middle of a spherical mirror, if you take light ray parallel to the principal axis, it will go through the focal point. It will be reflected through the focal point. In reality, it wouldn't, and so we'd get this thing called aberration. You get an aberration from it. 6 diagrams, 5 diagrams. We need to learn how to draw them. So, what I'm going to do is, and I can't, this is the bad thing about this. I made a mistake and I made my diagrams too small. They're okay when I'm using the overhead projector because I can zoom in on things. Well, we're going to practice it so it's not so bad. I have mirrors. I don't want to show them curvy because that means my diagram's going to be really messed up. So I want to show them like there's a straight line. You know, a little bit of curvature approximates to a straight line. But I want to give an idea of what kind of mirror it is, so I put little ears on it. So rather than a concave mirror where you look into it like that, concave mirror, a shaving mirror, a makeup mirror, that kind of thing. I'll show it as a flat surface with a little bit of curvature at the edges, and a convex mirror, which is like the shoplifting mirror you see in stores and all that kind of stuff, the rear view mirror and all that kind of stuff. It's really like that, and you look in that direction, but I'm going to show it as a straight line with these little ears on. Okay. There are 3 distances or points that I can characterize for any of these mirrors. The center of curvature, the focal point, and the point where the principal axis meets the mirror. I know the distance is always, 1 to 1. Yep. I can use these 3 points as positions. So I can say, let's consider an object that's between V and F. Or let's consider an object that's between F and C. Or let's consider an object that's beyond C. And they'll all behave pretty much the same in any given class. So all the ones that are near will behave the same. All the ones that are in the intermediate distance will behave the same. And all the ones that are in the far distance will behave the same. I avoid key points like I will not put my object on the focal length or on the center of curvature because there I cannot get an answer. And if I try this physically, I will get no focus whatsoever. So I got 3 choices. In front of the focal length, between the focal length and the center of curvature, beyond the center of curvature. Boom, boom, boom. The position of those can vary from mirror to mirror, but the diagrams will be the same style. In each case, I'm going to take 3 rays. I'll take a ray that goes along the bottom of the center, from the object along the bottom, along the principal axis, and it will bounce back on itself. I will take a ray which goes parallel to the principal axis, and that will always be reflected through the focal point. I will take a ray which goes from the top of the object to the mirror, and that always bounces back through the center of curvature. Now, this is where this diagram runs into a bit of a problem. If I have a mirror and I truly have it as a radius, and I take a ray which goes from the top of the object to the mirror and hits the mirror at 90 degrees, it's on a radius, and so it bounces back through the center of curvature. So an object, a ray from the top of the object which hits the mirror at 90 degrees bounces back through the center of curvature. But because I chose to draw this as a straight line, it looks like that's not the case in this diagram. So there's abstraction there. I'm kind of like using a bit of cheating there. The alternative is I try and draw my diagrams using this more realistic mirror, and it messes up my focal point stuff. So it's better to just draw a straight line. So although this does not look like 90 degrees, you've got to just believe it's 90 degrees. What you do is you put your ruler on your top of your object, you put your ruler on your center of curvature, and you draw your line. You don't worry about, you don't construct it by how it behaves here, you construct it by those 2 points. In each case I do these same 3 rays. I always get the same, let's change the colour of my pen so that you can see what I'm adding. You always get the same bottom ray. It always goes backwards and forwards along the principal axis. I always get, well, the same, not the same ray, but the same idea behind. The one that goes parallel to the axis always goes along and then through the focal point, and along and through the focal point, and along and through the focal point. And then my third ray always, let's do this in black, my third ray always goes through the top of the object and the center of curvature, through the top of the object and the center of curvature, through the top of the object and the center of curvature. Now notice the difference, quite difference in this third diagram. And I always ask myself, because I put the bottom of the object on the axis, I don't need to worry about that. I always ask myself, where do these 2 top rays converge? And in the first diagram, they actually diverge. So I back project them, and where they appear to converge, there's my image. And in the second example, oh my word, they do converge. And there's my image. And in my third example, oh, they do converge, and there's my image. And the images are very different in character. This first image is going to be virtual because it's not really there in terms of the light doesn't go there. It's upright because it stands upright. And it's magnified. It's clearly much bigger than the object was. Now ask yourself, you're using a shaving mirror, or you're using a makeup mirror, you see a big image of your chin or your eye, yeah? Yeah? It's magnified. It's upright. Your nose is not above your eyes. It's like the right way around. Real or virtual doesn't matter. You can't tell with your eyes, you just look, yeah? So, if you were to take that same mirror and you hold it further away from yourself, what you would see is, you would see an image, but it is upside down. Now, there's a bit of a problem. If you're using your face as the image, then a face as the object, then the image is kind of behind you. So that's a bit hard to see just using a mirror. But if I was to hold my thumb there as the object and move my thumb backwards and forwards, I could see this effect, And you'd see that the image would appear to be, you still look in the mirror to see the image, but the image would appear to be kind of like upside down, magnified again. So it would be a real image, it would be inverted and magnified. And then finally we'd have this guy, and this would be a tiny upside down image. And it would be real, it would be inverted, and it would be demagnified. So they're all a bit different. Okay? I would like you to be able to draw these diagrams. So what we're going to do is we're going to pause on the tape, because I can't put this on the tape, and we're going to practice, okay? So I'm going to pause this. So we're back, and we spent some time, we just drew out a couple of diagrams. One we did for the concave mirror, and one we did for the convex mirror. And what we found out was, the more carefully we draw our diagram, in a way the better our results turn out. We could work out the magnification by saying that our magnification equal the image height over the object height. And it also, we can work out our magnification from our Q over P And we got reasonably similar answers depending on how well we drew it. If we drew it perfectly, we'll get exactly the same answers. Bigger diagrams always work better than smaller diagrams, etc., etc., etc. So we saw that there were these three for the concave mirror. For the convex mirror, it turns out that first of all, your focal length is behind the mirror and your eccentric curvature is behind the mirror. But it turns out it doesn't matter where you put your image in front of the object, in front of the mirror, I'm sorry. It doesn't matter where you put your object in front of the mirror, whether it's near or far away. You get the same structure, which is basically you're going to get a virtual, upright, demagnified image. It might be bigger, it might be smaller, but it's going to be the same diagram. The actual angles might change slightly, but it's the same diagram. It's not like here where you got three radically different diagrams depending upon where you were. For this, you get the same diagram. It's always upright and demagnified. If you think about it, when you look in your rear view mirror, you never get a flipped version of what's behind you. It's always upright and it's always smaller, because that's the way they work. And that's why it's so useful as a rear view mirror. If it did this jumping around like the concave mirror does, it would be a disaster, because you'd get a flipped image depending upon where the car behind you was. It would be awful. So in a way, kind of the concave mirrors are more complex than the convex mirrors as far as ray diagrams are concerned. We can do the same mathematically. And I'm going to test you on both skills. And so there's two equations we need to know. 1 over P plus 1 over Q equals 1 over F. And then I remember, oh yeah, the focal length is basically, focal length is half the radius of your spherical mirror, so it's 2 over R. I remember this bit really well, because it applies to concave mirrors, convex mirrors, and lenses. So I learned this bit really well. And if it's given in terms of the radius, distance to the center of curvature, I can figure out what my focal length is from there. Yeah. So, and then the magnification equals my image distance over my image height over my object height, which I've learned. But then it's actually interesting. It's not Q over P. It's minus Q over P. And that's because we need to be careful about signs. So you not only need to know the equations, you need to know the sign conventions. And they're kind of logical. The object distance P is positive if the object is in front of a mirror. Well, okay, so here's your mirror of some kind. And if your object is over here, it's positive P. That makes sense, yeah? P is negative. I really don't need both of these, do I? If it's one or the other. Q is positive if the image is in front of the mirror. Oh, okay. Sorry, I got to just turn that off. Now, let's think about that. You can express this in a whole bunch of ways. If your object is in front, it's positive. If your image is in front, it's positive. You could say Q is positive for a real image, because real images are in front of the mirror. So you can define it either way. A real image will be positive Q. If it's to the right of if it's to the left of the mirror, if it's in front of the mirror, it will be a positive Q. Okay. So those two, and otherwise it's negative. And then what about F and R? F is the distance to your focal length, and R is the center of curvature distance. If it's, again, look at your diagram. If they are in front of the mirror, they are positive. If they are behind the mirror, they are negative. Now, what does that mean? That means if it's a concave mirror, they're positive. If it's a convex mirror, they're negative. Assuming you're working from left to right. Yep. So, and then M is positive, the image is upright. If M is negative, the image is inverted. So now, let me just let's bring a page in here. Let's look back at our two examples. So we're going to take the concave mirror. So basically we had a concave mirror, and what we said was, in my case, I said let P equal 5 centimeters and let Q equals 9 centimeters. And I want my focal length. My focal length, I said, was equal to 3 centimeters. Okay, so that's what I'm given. Well, no, let's actually stop that. I'm given those two. I know my P, I know where to put my object, I know my focal length. Okay. Let's find Q. 1 over P plus 1 over Q equals 1 over F. So 1 over 5, I can work in centimeters as long as I stay in centimeters, plus 1 over Q equals 1 over 3. So 1 over Q equals 1 over 3 minus 1 over 5, which equals 5 over 15 minus 3 over 15, which equals 2 over 15. Yeah. So Q is equal to 15 over 2, which equals 7.5 centimeters. Yep. I'm just going to check my ruler and just see that I didn't measure that wrong. No, I drew it. A slight difference in my drawing. Okay. So let me just double check that. 1 over P plus 1 over Q. My P, was my P 5 centimeters? That's where I wasn't very careful the first time round. Yep, okay. And then that focal length is I'm a little bit out of my drawing. I got about 3 1/4 for my focal length. Well, it should have been 3. Okay, so I got that. And then the next thing I want to do is want to work out my magnification. My magnification is equal to minus Q over P, which equals minus 7.5 over P is 5, which equals minus 1.5. Is that right? Am I right on that? Minus 1.5. So those are my two answers. Let's just interrogate them a little bit. So the first thing that happens is this is a positive Q. And what does a positive Q mean? Positive Q. I have a problem here. Just bear with me 1 second. Let's have a look. That's going to be 15, so that's going to be 5 over that minus 3 over that, which is positive. So positive Q means that it is in front of the mirror, which is I'm going to pause for a second because I'm digging a hole for myself. Yes, sorry. So we just figured out what I'm messing up. The example I picked to talk about, where I took the values from of this, the example I'm using is the convex mirror. And so for the convex mirror, I thought I was looking at a concave mirror. For the convex mirror, this is minus 3. This is convex. So this would be a minus 3. So that would be a minus 3. So that would be a minus 5 over 15 and a minus 3, which makes a minus 8 over 15. So my Q is equal to minus 15 over 8, which equals minus 1 point, what was that?
Negative 0.53.
No, it's 15 over 8. You got to flip it. I want to find Q.
Oh, okay, then divide that by 1.
Minus 1.87. Okay,
Yeah,
87
1.87.
centimeters. Okay, and then when I take this over here, so I've got to start this all over again. So M is equal to minus 1.87 divided by my P. My P is plus 5, which equals plus 1.87 over 5, which equals be basically 9.
Negative 0.35.
That's not right though.
Oh, let me just do the math and then I'll jump in. Let me just do the math and then I'll come back, because otherwise. So what will this work out to be?
1p has to.
Zero
Just let me do the calculation, then I'll think about it. Okay, 0.375.
375.
So what's going wrong?
It's inverted.
Negative.
Yeah, it's supposed to be, like, in the diagram, the
And
image
it's
is inverted.
positive. Yeah,
So it should come out to a negative.
Yes, it should come out to a
One,
negative.
the thing is 1/3 has to be positive. At the beginning of the equation, at the top.
no, it's not.
It's a convex mirror.
Yeah, but if the equation says that 1p,
Let me go to pause. Let me just. So we're going to have a second go at this. I'm going to try and do it consistently this time, because I got bits of both diagrams. So this was my. So this is my image and this is my object. And what we had here was P equals 4.5 centimeters. And that's in front of the mirror, so that's a positive P. And we don't know what Q is. We want to try and find Q out and check it versus our answer. So we'll put down a question mark. And then we're going to turn around and say that our F, and our F, now this example that I picked up, this is a convex mirror. Okay, so this is going to be a negative value, and it's going to be minus 3 centimeters. So there's my starting point. And I say 1 over P plus 1 over Q equals 1 over F. So that's 1 over 4.5 plus 1 over Q equals 1 over minus 3. So 1 over Q is equal to 1 over minus 3 minus 1 over 4.5. So let's make this common base a 9. So that would be 3 over 9 minus 2 over 9, which equals minus 5 over 9. I think I did that right.
It's 1.79.
So that means Q is equal to minus 9 over 5, which equals, I think, minus 1.8. 1.8. It's 4 over 5, so 1.8 is my image distance. Centimeters. And what that tells you is there is a virtual image because it's behind mirror. Okay? So that's what that tells you. And what we got experimentally when we measured it was we got 1.7 centimeters as opposed to 1.8 in our diagram. Yep. And then we have our magnification. Our magnification is minus Q over P, which equals minus 1.8 over my P, and my P was plus 4.5, which is plus 1.8 over 4.5. And what does that work out to be?
right.
0.4.
0.4?
Yes.
0.4 for our magnification. No units of magnification. And that, again, what that tells us, that positive sign tells us is that it's upright. Yep. So it's upright. So sorry about the pain, but we got there in the end, okay?
No pain, no gain.
Yeah. So then, as an exercise, let's do the next one, just to sort of sub that. So I'll give you a second to copy that down, and then we'll do the next one, okay? Because in the test, I'm going to give you a ray diagram, and I'm going to give you one of these, not the same problem. So you've got to be able to do both skills. So then let's look at this one. Oh, it could be a mirror, could also be a mirror. We're not at the mirrors yet, but the next one. So the next one was basically, we have this. This is concave. There's our focal length. There's our center of curvature. We get a ray that goes through the focal length. We get a ray that goes through there. And there's our image. What we said was P was equal to 5 centimeters. And we said that center of curvature was equal to, 6, so F is equal to 3 centimeters. Now, this is a concave. Concave means that's a positive. Concave. Yep. Positive, because this is in front. Yep. 1 over P plus 1 over Q equals 1 over F. 1 over plus 5 plus 1 over Q equals 1 over plus 3. 1 over Q equals 1 over plus 3 minus 1 over plus 5. 1 over Q is equal to 5 over 15 minus 3 over 15, which equals 2 over 15. So Q is equal to plus 7.5 centimeters. And what I said in this thing was, I said it was 9 centimeters because of my diagram. But that means there that it is real. And it is real. I think what I did was I picked up the wrong paper halfway through that last problem. Which is always embarrassing.
So the real image is in front.
Real image is in front of the mirror, yeah. And M equals minus Q over P, which equals minus plus 7.5 over P, and P was plus 5. So that would be minus 1.5 as my magnification. And we got 1.6 or 1.8. So am I right on that? It looks like I'm right on that. And that there means it's inverted. And it is inverted. Cool. So, 2 skills. Let me check my number of minutes. 42 on the right. Cool. So now we do the same thing again, but we do it for lenses. And for lenses, we don't have a center of curvature, so we just talk about the focal length. And it turns out the focal length is symmetrical. So the focal length is in front of the lens, and the focal length is also behind the lens. Okay? So, again, we put our object sitting on top of the principal axis. And what we do is we say the object is in blue. And we draw one. So we have 2 types of lens. We have, this is what we deal with. We have a lens which is fat in the middle and thin on the edges. And that is called a converging lens. It's like having 2 prisms, like that. And it causes light that's going parallel to converge into the focal point. And then we have, this is a diverging lens. It's like having a prism that's like that and a prism that's like that. And the light goes away. It seems to diverge away from a focal point. So we call the fat in the middle lens the converging. We call the skinny in the middle lens the diverging. If you think about a magnifying glass, is it a converging lens or a diverging lens? A converging lens. If you have, it's hard to tell with glasses, because with glasses they tend to use lenses that look like that. They don't tend to use lenses that look like that. But there's a difference between that and between This is fat in the middle and skinny on the outside, and this is skinny in the middle and fat on the outside. So you can get diverging and converging glasses. If you wear glasses and they make the world look bigger, or you're looking at somebody who's wearing glasses and their eyes look bigger in the glasses than they do when they're not wearing the glasses, then they have basically the equivalent of a converging lens. If they have glasses which make their eyes look smaller, or they see the world as smaller, then they have the equivalent of diverging lenses. The way we represent them is with a straight line now. Converging lens, put the two prisms like that, and a diverging lens, put the two prisms like that. So that's the way, shorthand for it. In each case, we have a focal point in front and a focal point behind. The rules are the same. You're going to have a ray which goes along the principal axis. It will not reflect. It will continue all the way through. So in every case, I'm going to have a ray that goes along the principal axis. I'm going to have a ray that goes from the top of the object parallel to the principal axis, and for converging lenses, that ray will converge through the focal point. Will converge through the focal point. For a diverging lens, the ray will diverge from the focal point. Diverges from the focal point. So for the converging lens, I'm using that focus, and for the diverging lens, I'm using that focus. And then your third ray always goes through the center of the lens. Because when you go through the center of the lens, nothing happens. Why? Because the glass on the front and the back is parallel, so it just goes straight through. So we see different outcomes. These two never converge, so we've got to back project them. They appear to come from here. My image. Now we've got to be careful, because my image is to the left of the lens, but it's not real. It's virtual. Because the rules for lenses as far as to the right or to the left are kind of different. So it's a virtual image because the rays do not go through there, but it is to the left of the lens. Here, the image is to the right of the lens, but it's real. So that in front of and behind the lens is opposite to be in front of or behind the mirror. And you can turn around and say, I expect my image to be in front of the mirror. I expect my image to be behind the lens. Does that make sense? So positive is what you expect. If you get what you expect, it's positive. For diverging, this is real. I'm sorry, this is virtual, and this is virtual. So again, for diverging, not much change. For converging, big change. Yep. We got time. Do you want to practice? Shall we do a ray diagram?
I have a question.
Yeah.
Okay, the top right instance. Okay, you're looking at something really far away with a, with a skinny on the edges lens.
Yeah.
Right?
A magnifying lens.
And this is just from experience. If you're looking at something super far away, you're looking at it through a lens, like a telescope. If you go left and right are flipped. If you tilt to the left, the image moves to the right, but up and down don't change.
Oh.
Is there something else at work there?
No, I don't know about that. I would want to see that, actually. Okay. Because it's symmetrical. There's all these things about left and right and up and down. There's the thing about the mirror. The person in the mirror holds their right hand up because you hold your left hand up. But so your reflection holds the opposite hand to you. But if you wiggle your head, your toes don't wiggle. So how come you don't get this like symmetry vertically as you do horizontally? And it turns out the fallacy is that you're interpreting what you see as a person. You know, the arm that's on the right of you is on the right in the image. It's not the left hand of the person, but you interpret it as the person looking the other way. So you say, I raise my right arm, he raises his left arm, because you're thinking about him facing the other way. I raise my arm on the right of the mirror, he raises his arm on the right of the mirror. I raise my arm on the left, he raises his arm on the left. I wiggle the thing at the top, he wiggles the thing at the top. So there's this interpretation. But I'm not familiar with that thing where you move the lens.
It's only with a refracting.
So show me that. And that's,
Okay.
it's, so I can't comment on it, I don't know. Now, yeah, okay. So this raises the issue of a magnifying glass. If you want to use a magnifying glass, you want a big upright image, so you must have the object be within the focal length of the magnifying glass. You can't use a magnifying glass to look at a distant object, because what would happen is, yeah, you'd have to be, first of all, a long way away from the magnifying glass to actually see the image, and it would be inverted. Okay, what tends to happen is you have your head somewhere here, and it's confusing what you see. Okay, now if you were a long, long way away, this thing would all be very small. So it'd be like, you know. So we can't just take a magnifier and make it into a telescope. It's not going to work well at all. So let's stop there. So we're back, and we did a diagram, and we did the diagram, which is basically this diagram here. So now let's go through, and again for the mathematics, so this is the mathematics we're interested in. So for the mathematics, same equations, 1 over p plus 1 over q equals 1 over f, and m is equal to basically minus q over p. And now for the mathematics, we got a little bit of a different sign convention. The p is positive if the object is in front of the lens. Well, that's what you'd expect. And the q is positive if the image is in the back of the lens, which is what you'd expect. And forget these r's. The f is positive for a converging lens, and it's negative for a diverging lens. So there's a bit of memorization there. The way I remember it is I teach you about the concave, and then I teach you about the convex, cave, and then convex, and that's positive and that's negative in the order I teach them. And I teach you about the converging and then the diverging, and that's positive and that's negative in the order that I teach them. So, you know. And what I can do is, let's just take this quick example and see if we can work out the numbers for it. So let's go here. And so in this example we have, there's my symbol for my converging lens. I have this guy inside the focal length. It comes along, converges through the focal length. There's the focal length behind. Stop it. There's the focal length behind. We go through the center of the lens. These guys never match up, so they come here. And we have a virtual magnified upright image. So there's my image. So that's what I'm looking at. And I know that my f is equal to, well, it's 3 centimeters, but it's not just 3 centimeters, it's a converging 3 centimeters. So I know that's a positive 3 centimeters. And I know my p, I chose to make that, it's going to be in front of the lens. There's my object. So that p is in front of the lens. That's a plus 2 centimeters. And I want to find my q. And I go 1 over p plus 1 over q equals 1 over f. So 1 over plus 2 added to 1 over q equals 1 over plus 3. So 1 over q is equal to 1 over plus 3 minus 1 over plus 2, which equals 2 over 6 minus 3 over 6. which equals minus 1 over 6. So Q is equal to minus 6 centimetres. And we got 6.2 in our ray diagram, so 6 centimetres is not bad. And the negative sign there, the negative sign means that it is virtual. And for a lens, that means it's in front of the lens. Okay, so that's consistent. Then M is equal to minus Q over P, so M is equal to minus 6 over P, and P is plus 2, so that's going to be minus 3. And with our ray diagram, we got either 3 or 3.1, depending upon which way we did it. And that negative sign, oh, sorry, no, minus 6.
It's
That's
not the negative
so minus Q, and Q is minus 6.
but it's not real instead of.
So that's what I'm saying. It's a positive value, okay,
It's upright, right?
which means it's upright. The real or virtual is done there.
So if it is virtual, it has to be negative.
If that's a negative sign, it's virtual. Yeah. On the magnification, it's the upright or the inverted, and this is a positive 3, so it's an upright. Yep. So these give you virtual real, and this gives you upright inverted. Cool. So there's the match. I'm going to stop there.